Okay, this is an HCl molecule. When you dump it into the water, what does it turn into? You end up with H plus, separate from Cl minus. Okay, so just like ionic compounds, acids dissociate in water. $75. And the most important ion of all in the acid is the H plus ion, okay? That's what makes it an acid, is that it has that H plus ion floating around on its own in the water. Now, if we have bases, bases don't contain H plus. What do they contain? OH minus. So bases, when you put them into water, they dissociate. What does it mean to dissociate? To break apart. When they're put into water, and they yield the hydroxide ions. So you can see here we have some NaOH, which is a solid, and it splits apart into separate Na ions, and most importantly, OH ions is what makes it a base. Okay, and so you can actually see a little picture here. We have a little NaOH crystal lattice. But when it dissolves, the Na is no longer together with the OH. It is separate. Does this seem familiar, like something we might have done last day? I will come back here, but just let's pop back for a moment and take a look at the double replacement. Oh, and I remember I had, yeah, so it's sideways for whatever reason, I don't know, and I don't know where I put the actual good copy of it. So regardless, we had these pictures. They were on the right side. They were tilted the right way. But do you notice that you have particles that are all floating around separately, and then you had particles that perhaps maybe came together? Yes? Or you had particles that were floating around separately, and then only some of them came together. It's going to be exactly the same sort of thing for an acid and a base, but we're not going to make a solid. What did we call that solid? That solid was called a precipitate. So we're not going to form a solid here, but we do need to form something. We need a new substance. What new substance is formed when an acid and a base react together? What are the products of an acid and a base reacting? A salt plus water. And water is our new substance. Just like the precipitate was the new substance in a double replacement reaction, the water is the new substance in a neutralization reaction. Okie dokie. So what's going to happen? And then we have salts, okay? And what is a salt? NaCl is table salt, but there's lots of different kinds of salts. A salt is just an ionic compound. So there is NaCl, but I could give you AgNO3, and that would be a salt. I could give you Ca3PO4, 2, and that would be a salt. Okay, any ionic compound that is not a base, that does not contain hydroxide, is a salt. So salts are all ionic compounds that do not contain hydroxide. If it contains hydroxide, it is a base, okay? Now, I don't think you probably we'll just leave that for now. I'm just going to give you a couple of examples. They are on your page already. We are going to write the dissociation equations. If I have NaCl, which is a solid, and then I dissolve it in water, so I'm just going to put the water there as like dissolve in water. What would we write as our products there? And if you're having trouble thinking of it, you can just look at this picture right here, because we have solid salt here. This is the NaCl solid. And now we are dissolving it in the water. And what do we get? We get Na plus, and we get Cl minus. So basically when we're dissociating, we are just separating the ions. Okay, and what state would each of those be? They would be salt went into the water, now it's in the water, aqueous. Okay. HCl. HCl is a gas. Okay, if it's not dissolved in water, it's gaseous. You don't need to know that, it'll tell you. But if we dissolve it in water, what do we get? You get H plus, and you get Cl minus, because basically we are still just separating the ions. And of course, these would also just be aqueous and aqueous. And just to show you what happens when we have a ratio that's not 1-to-1, these are both 1-to-1 compounds, but we could have something like CaOH2 when it dissolves in water. What would we get? Well, we need to separate the ions, so we're going to end up with calcium. So it's going to be Ca2 plus. Yeah, we have to put the two OHs separately because they're not stuck together holding hands, okay? It's not OH2, okay? Aqueous, aqueous. Similarly, if we had a salt, CaCl2 dissolved in water, the Ca would be separate. And it's really, really tempting because we know that Cl2 is one of the diatomic molecules, right? It's so tempting to write Cl2. Is that correct? You can tell from my tone of voice that it is not correct, and that's because it's only Cl2 when it is neutral. Cl2 is neutral, and it is on its own. When CaCl2 is dissolved, it's still part of the calcium chloride compound. It is not really on its own. Even though the ions are floating freely, if you were to evaporate the water, it would recondense into calcium chloride salt, into the crystal lattice again. So it is absolutely not Cl2. It would instead be Cl minus. But of course, we do have to take into account that there is that little 2 there. How do we take that into account? What do we need to do? We put a 2 right here, okay? So just take a few minutes and try the questions on this page here, okay? Classify things as either acid, base, or salt, and then write the dissociation equations for these guys here. Keep your polyatomic ions together, okay? Polyatomic ions don't like separate out into N's and O's and things like that. Anytime anything dissolves in water, it is. Sorry, it's all good. Okay. If you finish, that's great. If not, you can finish the rest of them for homework. Okay. Page 77, 77. So a neutralization reaction is really just a double replacement. The only difference is that instead of having two salts, salt plus salt, you'll have acid plus base, okay? So this one is salt plus salt. This one is acid plus base. And in double replacement, you start with two salts, you finish with two salts. Neutralization, you finish with a salt and water. Okay, so you finish with this, you start with an acid and a base, you finish with a salt and water. But if you know how to predict the products of a double replacement reaction, you also know how to predict the products of a neutralization. Do you remember what the pattern is to predict the products of a double replacement? Combine the outside ions and then make sure you balance the charge. Then you are going to combine the what ions will you combine next? The inside ions. And of course, again, you're going to make sure that you balance the charges, okay? Balance the charges. And then of course you balance the reaction, okay? 3, balance the reaction with coefficients. Okay, so if you know how to do a double replacement, you know how to do neutralization. Combine the outside ions, combine the inside ions, combine the outside ions, then combine the Okay, and what the heck are those outside and inside ions? Let's take a look at an example to remind ourselves of what that means. Okay, so we have sulfuric acid. So we need to, I'm just over here on the side going to figure out the formula for sulfuric acid. It's an acid. So what is the positive ion in an acid? I have H plus. Now I have sulfuric acid. Ooh, ic acids are what kind of ions? Ic acids come from 8 ions. I ate something icky, yes? So we are looking at sulfate. So sulfate, we can look that up on our polyatomic ion chart. It is SO4 2 minus. So we have sulfuric acid, we have H plus, we have SO4 2 minus. So what is the formula for sulfuric acid? That becomes H2SO4. So that's what we're going to write here as one of our reactants, H2SO4. Plus, our other reactant is aluminum hydroxide. Aluminum is 3 plus. Hydroxide is -1. So what's the formula? AlOH3. Okay. So we now have H2SO4 and we have AlOH3. Those are our reactants. The very first ion is one of the outside ions. The very last ion is one of the outside ions. And we are going to go from left to right. Those are our outside ions. The Al and the SO4, those are the, what are those? The inside ions. Inside ions. And if we go forwards for the outside ions and backwards for the inside ions, we'll have the cation in front of the anion, which is the way that we want it. I mean, you don't have to think about it that way, but it's somewhat helpful. It always means if you go forwards on the outside, you'll always have your cation and then your anion. If you go backwards on the inside, you'll always have your cation first, then your anion. All right, so our products, we need to combine H and OH. So H is positive, OH is negative. So these right now we're doing our outside ions, H and OH. What do you get if you put H and OH together? You get water. I'm actually, because it makes balancing easier, I'm going to write it as HOH. I can change it later if I want to, but I don't have to. Okay? HOH. Our inside ions, aluminum and sulfate. We have Al 3 plus, and we have sulfate SO4 2 minus. Would it be okay to just write it like this, AlSO4? Is that cool? Not cool. Very uncool. Very uncool. It's not balanced. And balance is I don't know what I'm trying to say. Never mind. Okay. That did not go well. Okay, so we have aluminum, and it'll be Al2SO4 3. That'll give us a balanced charge. So let's get rid of that because that's ugly and wrong. Al2SO4 3. Hooray, we've predicted the products. Are we done? No, because we need to combine the outside ions, balance the charges, combine the inside ions, balance the charges, and now we need to balance the reaction by using the coefficients. So, do you remember who it's good to look at when you're starting to balance one of these guys? Balance your most complicated compound first. So we're going to balance our aluminum and our sulfate. This is getting very crowded now. Maybe I'll write in green for the next one. Okay, so we have aluminum. I need 2 aluminums. So let's put a 2 in front of the AlOH3. We need 3 sulfate. So let's put a 3 in front of the H2SO4. And now you can either balance the H or you can balance the OH, and it won't matter. Whichever one you choose, the other one will just work out. Okay, so shall we balance the H this time? How many H's do we have on the left-hand side? We have not just 2, we have 3 times 2, which is 6. How many hydroxides do we have? We have 2 times 3, which is also 6. All done. And you can rewrite the HOH as H2O if you want to. Is good? Okay. Carbonic acid was titrated to completion with sodium hydroxide. Does it matter if you don't know what the word titrated means? No, you can just be like, that's some big word that I don't know yet. We will actually, on our very last day, be doing a titration lab. Okay, it's quite fun. All I need to know is that these 2 things are my reactants. Carbonic acid is based on which ion? Carbonate. So that is CO3, 2 minus. It's carbonic acid, so who is the other ion? H. So the formula for carbonic acid is going to be H2CO3. Was titrated, whatever that means, you'll learn it later, with sodium hydroxide. Sodium has a +1 charge. Hydroxide has a -1 charge. Oh, that's nice and easy. So that's just going to be NaOH. How do you predict the products of a neutralization or a double replacement? Combine your outside ions. And you will combine your inside ions. And you know what? If you wrote your ions over on the left like I did, you can be like, okay, sodium is going to get together with carbonate, right? And hydrogen is going to get together with hydroxide. Ooh, how lovely. So if we have sodium getting together with carbonate, these 2 guys here, Na plus CO3 2 minus, that's going to be Na2 CO3. We have HOH. Okay, +1 -1, so it's just H and OH. So that's H2O, but I'm going to write it as HOH. Okay. Are we balanced? No. Let's pick our most complicated formula, Na2CO3. I need to have 2 sodiums. I just need 1 carbonate. And so all I need to balance now is either the hydrogen or the hydroxide. I have 2 hydrogens and I have 2 hydroxides. So if I just put a 2 there, everything is hunky-dory. One final example to look at states. We have HClO4, which is aqueous, and BaOH2, which is aqueous. Our outside ions, H is getting together with OH, that's easy. HOH. And then BaClO4. BaClO4. You're right, I'm waiting to see if anyone else notices. It's wrong. Why? Why? Yeah, we need a 2 because it's barium 2 plus. And we have chlorate O4. Yeah, and it's just minus. And so we would need to have a 2, which would mean we would also need to have a coefficient of 2 to give us 2 chlorates. And that gives us 2 hydrogens, so that's going to give us 2 waters. Okay? Now our states, the water will always be liquid. And in theory, you should be able to look this one up on your solubility chart, but I don't actually think chlorate is on your chart. But chlorates are always soluble, so I'm just going to give you that one. There you go. Okay? So yeah, that's it. All right? So I would like you to try some of these here. Okay, and yep. Then I'm actually going to go grab, what am I grabbing? I might grab stoichiometry for you. Ha, ha. Hi, thank you. Yes. Do you guys have a purple page yet? I'm trying to figure out what color page to give you. They make your life easier. Yes.
No sleep. I'm
Okay.
so toast.
Yeah.
I talk to less the best I can. Am I? Is there much more? Not
Um,
like a stew, or I assume it's online.
you know what? It's being recorded. You can watch it online. It's no problem.
Just on YouTube. Is it on your YouTube channel?
It is on my YouTube channel. You can also just go to Teams and it says lesson videos,
Okay.
and it'll be posted there.
Awesome.
Okay. Yeah. No, seriously, do it. Yeah. Yeah. Don't worry. Hello. I'll be right with you, Aaron. No, I don't want to edit file. Oh my god. File, print. That's so good. We'll worry about them some other time. We don't have enough time this year to worry about that too much, so we're just gonna be like, yeah. Okay. Cool. Don't worry about predicting the states. We don't have time to worry about that this year. Okay. So we're just gonna be like states. Wait, we don't know. We don't think. Okay. Just predict the products and don't worry about the states. unless it's a double replacement. Okay, and then you have to say which one is controlled. Okay? All right. We're screaming through the energy unit, or the reactions unit. We're going to visit page 98 today. Page 98. I'm actually skipping over predicting products of combustion reactions because it's always CO2 and H2O, so there's not really a lot to say about it, okay? Like you predict the products, it's carbon dioxide and water, and that's it. Okay, then you have to balance it, and it's the balancing that's the hard part, but you've practiced some balancing already. Page 98. This will be important for Chem 12, if you're taking Chem 12. Are you familiar with the terms kinetic energy and potential energy? Yes. Kinetic energy is the energy of motion. Potential energy is, what is potential energy? Stored energy. We can abbreviate kinetic energy as KE and potential energy as PE. That saves us a lot of writing. Do you know the law of conservation of energy? You cannot do what to energy? You can't make it, you can't get rid of it, you can't create it, you cannot destroy it. You can, but what you can do is you can transform it. It can be transformed from one form into another. So if we have a system, the kinetic energy plus the potential energy is going to equal the total energy, and the total energy will always remain the same. Do you know the unit of energy? That is the joule or the kilojoule. Okay, it's pronounced joule or kilojoule. So this part here, this is not going to be on any test, but it's sort of nice to know what do we mean when we say kinetic energy for molecules, right? And besides which, it's kind of fun because if you have a molecule, that molecule can vibrate, it can rotate, and it can translate. Now, I'll bet you can figure out what rotating is. What is rotating? Going around. So if I'm a molecule, right now I have rotational kinetic energy. Okay? If a molecule is vibrating, there are actually a few ways that it can vibrate. If I'm a CO2 molecule, and this is the O, the C, and these are the two O's, this is vibration. This is bending vibration. Okay? There's also stretching vibration. This is symmetric stretching. Actually, this is kind of good stretching. If you want to do it along with me, feel free. This is symmetric stretching. This is bending. Okay? It actually feels really nice on my shoulders. And then we finally have asymmetric stretching. And what happens is you can have a molecule that is vibrating and rotating, and maybe it's bending up and down and it's doing asymmetric stretching at the same time. And then you have to add in translation which means you're actually moving in space. So here I am, rotating and vibrating and moving in space. Okay? So that's a lot of different types of motion. Like I said, you don't need to know that, but it was a lot of fun and my shoulders feel like they've had a nice little stretch. So there we go. Temperature. Temperature is a measure of, and this is important, so I'll put stars here and here. Temperature measures the average kinetic energy. It does not measure the heat, it measures the average kinetic energy. Heat has an actually stupid definition in chemistry. I'll read it for you. You'll be like, oh, yeah? Thought it was just when something was hot. But here is the definition of heat. Let me find the index here, the glossary. Glossary. Where's my glossary? Oh, here we are. Heat. Heat is the flow of energy from a body at a higher temperature to one at a lower temperature when they are placed in thermal contact. So heat isn't the amount of hotness, it's not the amount of temperature. It is heat is the flow of energy from object A to object B. Object A is this lamp is very warm, yes? My hand is object B. I put them in thermal contact with each other and we have heat transfer. That is heat, it's the transfer of the energy, the flow of the energy from the lamp to my hand. I didn't actually touch the bulb with my hand because that would like burn me and not be very nice. Okay? Is water wet? Okay. So, the more kinetic energy there is, I don't know what's happening in the hallway, weird things, more kinetic energy, the higher the temperature will be. So if you have faster molecules, then you have more kinetic energy. What can you say about the temperature? It's higher temperature. If, on the other hand, you have slower moving molecules, they're not vibrating as quickly, they're not moving in space as quickly, they're not spinning as quickly, they have less kinetic energy and the temperature will be lower. Potential energy. Potential energy is stored in the atoms and the bonds between the atoms and can be released by various chemical reactions. Chemicals with a high potential energy are less stable, okay? They don't like being like that. There's probably a lower potential energy state that they could turn into where they'd be a little bit happier. It's like if you put a ball at the top of the hill, is that its most stable state? No, it'll roll to the bottom of the hill and that'll be a lower potential energy. That will be a more stable state. So if they have a low potential energy, that is a more stable state. If we take some kinetic energy and we transform it into potential energy, what is happening to the amount of kinetic energy? If we take some kinetic energy and we turn it into potential energy, what has happened to the amount of kinetic energy? It has gone down, okay? So the kinetic energy decreases. What does that tell you then about the speed of the molecules? The kinetic energy has gone down, so the speed has gotten slower. And if the molecules are moving slower, the kinetic energy is lower. What's happened to the temperature? The temperature has decreased. And the total amount of energy will, of course, stay the same. Okay? Total energy will stay the same. Now, the opposite will happen if we turn some potential energy into kinetic energy. What's happening to the amount of kinetic energy? Kinetic energy would be going up because we're turning potential into kinetic. Now we have more kinetic. That means that the molecules are going to move faster. Higher kinetic energy, faster molecules means that your temperature will increase. But the total amount of energy will, of course, stay the same. So let's say you have some reactants. Yes? Got some reactants. And they're in a chemical reaction and they have 2 kilojoules of potential energy. Okay, so the potential energy of the reactants is 2 kilojoules. Now let's say we have some products and the potential energy of the products is 12 kilojoules. Now remember, you cannot create energy, you cannot destroy energy. Where did the extra 10 kilojoules come from? Because we've got 2 kilojoules of potential energy, and after the reaction is finished, we have 12 kilojoules of potential energy. Yeah, it came from kinetic energy. What's going to happen to the temperature if we took some kinetic energy and turned it into potential energy? The temperature is going to go down, okay? So we take 10 kilojoules of kinetic energy and we transform it into 10 kilojoules of kinetic energy to give us 12 kilojoules in total, or sorry, that should say potential energy. And because we used up 10 kilojoules of kinetic energy, the temperature will get lower. Is good? Okay. Let's look at that in an actual reaction. We have the reactants, and they have potential energy is equal to 2 kilojoules. We have the products. The potential energy is equal to 12 kilojoules. What that means is that we had 10 kilojoules, and that is kinetic energy. And as it becomes products, it turns into 10 kilojoules of potential energy, which is now part of the products. Okay? So now those products are storing 12 kilojoules of energy. And because we used up kinetic energy, the temperature will get lower. Therefore, the kinetic energy decreases, and therefore the temperature decreases. So if temperature is decreasing, it's getting colder. Is this making sense so far? Now I'm going to throw it on its head, and I'm going to make it not make sense for a minute, and then we'll try and make it make sense again, okay? So now we call this kilojoules here, we call that the heat term. This is why it's confusing, okay? And what are we doing to that heat? We are absorbing that heat. What do things do when they absorb heat? You would think that they get hotter, but in this case, it's not, we don't have a flow of heat from reactants to products. We have the heat being absorbed and transformed, okay? So when we say that heat is absorbed, it's not just absorbed, it is absorbed and transformed into potential energy. So when we say we have 10 kilojoules of heat, we are absorbing 10 kilojoules of heat and turning it into potential energy. So there's actually less heat than there was before, which is why the temperature gets colder. Okay? So that's the trick. When we say that the energy is absorbed, it's not just absorbed, it's absorbed and transformed. This is our heat term. The heat, the 10 kilojoules of kinetic energy, but not just absorbed, the heat is absorbed and transformed into potential energy. What? RXN, our reaction. Friction reaction. And I don't know if you heard this term last year. Have you heard the term endothermic? This is an endothermic reaction, okay? This is an endothermic reaction. It absorbs heat, but it doesn't just absorb it, it also transforms it into potential energy. Therefore, the kinetic energy is getting lower. Therefore, the temperature is getting colder. When you absorb heat, you're not actually getting hotter. You're actually taking that heat and turning it into something else. Okay, I will put the homework on Teams, okay, because we're just about out of time here. It's just going to be some practice on double replacement neutralization, okay?